Imagine a future where artificial intelligence, AI, helps doctors spot patterns that are just, well, too subtle for the human eye. Predicting disease, maybe its progression years ahead, saving lives. It sounds almost like science fiction, doesn't it?
It really does. But that's the incredible promise, the hope behind AI in healthcare.
Moving medicine beyond those subjective kind of gut feelings.
Exactly, towards something more precise, more data-driven, real insights.
And that's precisely what we're diving into today on the deep dive. We're going to unpack something absolutely fascinating and honestly a bit counterintuitive. It's a challenge emerging right at the heart of predictive modeling in medicine.
Yeah, because despite all this incredible potential, this powerful technology might actually be building on a house of cards.
We've been looking at a really compelling commentary, and it highlights this critical, often overlooked problem. It's about how the very success of AI in healthcare
Paradoxically, yeah.
can end up corrupting the data it needs to work, making it harder, much harder, to build effective models down the road.
It's a tricky one. So our mission today really is to give you a clear understanding of this complex issue.
We've got some surprising examples lined up.
And we'll reveal what leading experts are suggesting we actually do about it.
Get ready for some real aha moments about just how interconnected our health data truly is. It's more tangled than you might think.
Definitely. So let's start with the basics. Modern medicine, it really thrives on pattern recognition, doesn't it?
Absolutely. Doctors piece together patient histories, exam results, lab work, how patients respond to treatment. It's all about finding those crucial patterns.
But some patterns are just, well, they're chaotic, or maybe too subtle, too fleeting. Even the best doctors can't reliably catch everything.
Like trying to spot early-stage pancreatic cancer from just routine blood tests.
Exactly. That's incredibly difficult, maybe impossible right now for a human. So, these huge questions, will a tumor spread? How long might someone live? Often it comes down to a doctor's experience, or like you said, that gut feeling.
Okay, so how does machine learning step in? How does it tackle that subjectivity?
Well, it offers a really powerful way to reduce it. We create these computer models, right? And they learn from just vast amounts of labeled data.
Labeled data, meaning?
Meaning data where we know the outcome.
Yeah.
So for instance, you feed it thousands of mammogram images. Some have tumors, some don't. The model learns to recognize statistical features linked to tumors.
Even features a human radiologist might not consciously pick up on.
Precisely. Features that aren't obvious to our eyes, but the model identifies these subtle cues that tend to go with one diagnosis or another.
Yeah.
It's pattern recognition on a massive scale.
And when you see that capability, it's no wonder interest has just exploded. Looking at the sources, the sheer volume of research is staggering.
Oh, it is.
In 2024 alone, over 26,000 studies on PubMed mentioned AI, machine learning, or deep learning in patient healthcare. That just shows the profound belief in this tech.
It really does. And the stakes are incredibly high. I mean, think about tumor spread, organ failure, these narrow treatment windows, having accurate knowledge of how things might unfold.
Yeah.
That can conserve resources, reduce suffering, and, ultimately save lives.
And it's not just research interest. The money is flowing, too. The global market for AI in healthcare projected over $46 billion this year.
And potentially hitting $200 billion by 2030. This isn't just academic curiosity. It's a massive real-world investment happening right now.
Okay, but here's the catch we talked about. Despite all the sophistication, any model, no matter how advanced, is still a source of uncertainty. How does that uncertainty become a problem?
Well, it cuts both ways. If you underestimate risk, you might overlook serious problems. That's bad.
Obviously.
But overestimating risk is also a problem. It leads to unnecessary tests, maybe interventions the patient didn't need, wasted resources. It's a really delicate balance.
And the sources point out something else crucial. These models don't just learn outcomes. They absorb the clinical decisions, the relationships, even the biases that are baked into the training data.
That's a huge point.
So what happens if those underlying conditions, those biases, aren't stable when the model is actually being used in the real world?
That's where things can really start to fall apart. A model's usefulness, right, it's typically judged by how well it generalizes, how well it works on new data it hasn't seen before.
Okay.
But if the patterns or the decisions or even the biases in the real-world setting are significantly different from the training data, the model can perform poorly or just fail.
Can you give us an example? Make it concrete.
Sure. Imagine a model built to answer the question, is this patient at risk of dying tomorrow? Now, that question means something fundamentally different in say, a rural outpatient clinic compared to a cardiac intensive care unit.
Totally different context, yeah.
So a model trained in one of those settings is very likely to perform badly in the other.
Yeah.
The context, the underlying normal patient data, it's just worlds apart.
So context is critical, but what about the basic quality of the data itself, even before context?
Oh, that's another massive issue. A lot of medical data sets are, frankly, small, or they're biased towards certain populations, or tied to very narrow groups.
Which means?
Which means there's a high probability that models trained on them will underperform or even fail once they're deployed out in the messy real world. But here's where it gets really interesting and maybe counterintuitive.
Okay.
The biggest threat to widespread adoption might not actually come from where the models fail outright. It might come from where they succeed.
Right. Let's dig into this success corrupts data idea, because that definitely twists your brain a bit. Most healthcare machine learning, it's built on the electronic health record, the EHR.
Yep, the EHR.
And the sources frame this as a kind of double-edged sword.
It really is. The EHR is, it's basically both the main source of training data for these predictive models and the system where the predictions get fed back to the clinicians.
So it's this dynamic database logging pretty much everything, right? Lab results, meds, notes, big events like infections or, sadly, deaths.
Almost every aspect of patient care. And it enables this kind of standardized workflow. You take data from the EHR, you train your models, then those models analyze fresh patient data coming in, predict risks.
And those predictions can then nudge doctors, right? Like prompt them to order a chest x-ray maybe, or start antibiotics for pneumonia risk before the classic symptoms even show up.
Yes, exactly. And this leads us straight into what's been called the sepsis paradox. It's a perfect illustration.
Okay, lay it out for us.
So imagine you have a model. It's designed to detect the early signs of sepsis. Ideally, the model flags the risk nice and early. It alerts the physician. The physician jumps in, intervenes swiftly with antibiotics or fluids.
And the patient doesn't develop full-blown sepsis. That's the goal. That's the win.
That is absolutely the desired outcome. This is the kind of positive impact we want from AI. Success.
Okay, so this is where it gets tricky. The patient's fine, doctor did well, hospital's efficient. Where's the hidden rub that the sources talk about?
The profound insight here, the real kicker, is because the physician intervened successfully, the patient didn't develop sepsis.
Right.
So that pattern the model originally flagged, the one linked to sepsis risk, is now recorded in the EHR, in the database, as being associated with a non-septic outcome.
Ah, so you've created a contaminated association in the data.
Exactly. That's the term used, a contaminated association.
So over time, as all these successful interventions pile up in the record, what does that do to future models or even retraining the current one? It sounds like the warning signs for sepsis start to look like they lead to good outcomes.
Precisely, because they do lead to good outcomes thanks to the intervention prompted by the first model. It effectively erodes the reliability of both the existing models and any future ones trained on that data.
Wow.
And this gets compounded by something else called model drift. Things change. Patient demographics shift. Standards of care evolve. New medications come out. Clinical practices change.
All of which can make a model's predictions less accurate over time anyway.
Right. That's model drift.
And normally, the fix for model drift is you retrain the model, right? You feed it newer, more representative data.
That's the standard approach.
But if that newer data is already corrupted with these false associations from successful interventions, what does that mean for retraining?
It makes retraining it effectively
Wow.
impossible, or at least incredibly unreliable. The source used a great analogy. It's like trying to teach a kid addition by saying 2 plus 2 is 4. Sometimes. But other times it's 3, but only when it's not 5.
The data becomes contradictory. You can't learn from ground truth that keeps shifting because you successfully altered it.
You got it. The ground truth itself has been changed by the model's own success.
And it's not just that retraining that specific model becomes impossible. Does this contamination have, ripple effects? Does it spread?
Oh, it absolutely does. Think about conditions that often occur together. Comorbidities, like pneumonia, acute kidney injury, AKI, and sepsis. They often track together. So a model that successfully helps prevent, say, pneumonia, might indirectly prevent the AKI or sepsis that often follows, which, again, introduces misleading associations into the EHR, not just for the pneumonia model, but for any future AKI or sepsis models too.
So one successful model can inadvertently mess up the data for totally different future models.
Exactly. And it gets even more complicated when you have multiple AI models running in the same hospital, maybe even on the same patient.
Right, like one model watching for ATI risk, another watching for blood clots. Different problems, but maybe they rely on similar lab values.
That's a perfect example. Both might look at things like creatinine levels or platelet counts. Now, if a doctor gets an alert from the AKI model and adjusts the patient's fluids or medications,
That action could change those lab values.
exactly, which could then render the predictions of the separate blood clot model obsolete or unreliable, because the input data it's using has been altered by an action triggered by the first model.
So, an intervention from one model can, as the source puts it, quietly disrupt another.
Precisely. Even if they're focused on totally different outcomes. And this is a serious problem because, honestly, current approaches to predictive modeling just don't really account for how these models interact with each other or with the human clinical decisions they influence.
This really highlights what the commentary calls a performance paradox, doesn't it?
It does.
If a model works perfectly and helps prevent an adverse event like patients don't die of sepsis because of early intervention, then its real-world performance might actually look like it's declining because the thing it predicts isn't happening as often.
That is the paradox. How do you even monitor these things after deployment?
Yeah, how do researchers tell if a drop in, say, sepsis rates after implementing a model means the model is working great, or if it actually means the model is failing and just not predicting accurately anymore?
It's tough. One way is to try and regularly compare outcomes. Look at periods when the model is active versus periods when it's inactive, maybe in different wards or over time. This kind of side-by-side comparison can help try and tease out if the model is truly effective or if it's degrading.
But you'd need to have some idea beforehand of what range of performance change to expect, right? If the drop falls outside that range, maybe then you suspect degradation.
Ideally, yes. But estimating that expected range in advance is really difficult because you've got model drift happening naturally, you've got variations in clinical practice.
And the real world isn't a controlled lab. You have multiple models, different doctors making different calls.
Exactly. Real-world patient care is messy. So those gold standard randomized controlled trials, RCTs that we use for evaluating drugs, they're rarely possible for evaluating multiple interacting AI models in day-to-day care.
So clinicians might end up having to choose between predictions from several models, some perhaps overlapping or even conflicting.
That's a real possibility. And as more models get deployed, the results we see from those initial isolated, tightly controlled studies become less reliable indicators of how they'll actually perform in the wild, interacting with everything else.
So you need to be cautious interpreting performance unless it's used in exactly the same controlled way it was tested.
Pretty much, which is often not the case.
Okay, and then there's another layer, external validation. Testing a new model on data from a different hospital or health system. That sounds crucial, right? To make sure it's picking up real biological patterns, not just quirks of its original training hospital.
It is crucial. It's a key step.
Yep.
But it becomes much, much harder when the data you're using for validation, that external data, might have already been influenced or shaped by previous models used at that hospital.
Okay. So if you don't know which patient needs in the test data were affected by earlier AI predictions.
Then your validation attempt could give you really misleading results. Let's say you're testing a new mortality prediction model. You test it using data from Hospital B, but Hospital B already uses a different mortality model that's been successfully preventing deaths.
Your new model might look like it performs poorly.
Right, because the original model might have already prevented many of the deaths your new model is trying to predict. It masks the true effectiveness of the new model.
And that's a serious worry, especially now that, privacy-protected medical data is increasingly shared, pooled in big databases used by industry partners.
It really is.
Yeah.
How do you validate or compare models reliably when the data landscape itself is constantly being subtly reshaped by the very tools you're trying to evaluate?
Okay, so we've painted a pretty challenging picture here. It really does sound like the foundations of that house of cards are getting shaky.
Right.
What are the potential solutions? How do we even start to preserve this clean data?
Well, the commentary used a fascinating analogy, low background steel.
Low background steel.
Yeah, so steel produced after the mid-20th century, after all the atmospheric nuclear testing, contains tiny traces of radioactive isotopes. It makes it unsuitable for really sensitive radiation detecting instruments.
Oh, okay.
So to build those instruments, manufacturers have to use low background steel, basically. Steel salvaged from ships or structures built before the nuclear era. Stuff that wasn't exposed.
So the analogy is, if healthcare data that's been touched by machine learning is potentially radioactive, like the source suggests.
Then clean, unaltered data sets, data from before widespread AI deployment, or somehow protected from its influence, will become incredibly rare and valuable, like that pre-nuclear steel.
Wow. That implies we need a really fundamental rethink across the board.
It really does. And it means everyone involved needs to understand these risks and figure out their role in managing them.
So starting with the doctors, the clinicians on the front lines, what's their role?
This is critical. They need to start systematically documenting any predictions that might influence patient care. Like, AI suggested X, I did Y based on that. This just isn't standard practice today.
But it's essential for tracking the influence.
It's absolutely essential. It's the bedrock for having any kind of transparency, accountability, and the ability to actually learn how these models are impacting care and data over time.
Okay, so that's the clinicians. What about the researchers and the people actually building these models? How do they need to adapt?
They have a lot to think about. They need to explore ways to modify data sets, maybe remove cases known to be affected by prior predictions. They need to look more into causal machine learning.
Causal ML, meaning trying to understand the why behind patterns, not just correlations.
Exactly. Building models that understand underlying mechanisms might make them more robust to these kinds of data shifts. And also leveraging foundational models, these large pre-trained models that can sometimes adapt to new tasks with less specific training data.
So building smarter, more adaptable models from the start. And then there's the idea of creating specific gold standard data sets.
Yes, that's seen as a really promising, maybe essential approach. Creating these carefully curated data sets. This could involve tagging patient records where model predictions definitely influence decisions, maybe doing retrospective audits to clean up data.
And crucially, using data from before AI was deployed in that setting.
Absolutely. Using that pre-AI data as a clean benchmark is vital. But these gold standard sets also need to be kept up to date, reflecting real-world populations and evolving standards of care. They can't be static snapshots.
This all sounds incredibly complex, though, especially for hospital administrators who are trying to manage potentially dozens of these models running at once.
Oh, the complexity for administrators is huge. They'll face tough decisions.
Yeah.
How many models should we run? How many interacting on a single patient? Which model takes precedence if they conflict?
That requires new infrastructure, new oversight.
Definitely. New infrastructure, new governance processes, and it carries significant financial costs that most health systems aren't really set up for right now. It's a massive operational undertaking.
And then there's this highly controversial theoretical solution the sources touch on, the idea of feeder sites. What exactly are those?
Yeah, that one is, the idea is you designate certain institutions as feeder sites where predictive models are deliberately not deployed at all, or maybe very minimally. The goal is to preserve a completely clean pre-AI data environment in those specific places.
And the thinking is, you could train models on that super clean data.
Right. If those feeder sites are similar enough to other hospitals, patient populations, clinical practices, then maybe models trained on their pristine data could be transferred or deployed elsewhere with minimal performance loss due to data contamination.
Okay, I can immediately see the ethical alarms going off here. You're talking about deliberately withholding potentially beneficial AI tools from patients at those feeder sites.
That is precisely the ethical dilemma. It raises fundamental questions about equitable access to care. Are you creating a two-tiered system? Some patients get the latest AI, others don't, simply to maintain data quality for the future.
For the collective good of future data versus the individual patient's right to the best available care today.
It's a very, very difficult balance. It really forces a hard conversation about the immediate benefits versus the long-term sustainability and reliability of AI in medicine.
Okay, so wrapping this up, what have we learned from this deep dive? It really seems like, yes, machine learning holds this incredible promise for medicine, but deploying it without thinking through these feedback loops risks trading long-term data reliability for short-term gains, building that house of cards.
I think that's fair. And the core takeaway, the single most crucial step everyone seems to agree on, is the need to systematically document when and how these model predictions actually influence clinical care.
Without that documentation, we're just flying blind.
Pretty much. Unable to properly train, retrain, or even truly evaluate these powerful tools we're hoping will save lives. That documentation is step one.
So, our final provocative thought for you, the listener. If healthcare information touched by machine learning really is potentially radioactive, as that analogy suggests, what fundamental shifts in medical practice and ethics and how we manage data will be required to truly build the learning health systems we aspire to? How do we ensure innovation doesn't inadvertently undermine its own foundations? What stands out to you as the biggest hurdle or maybe the most promising path forward here?